Let's define basis of a vector space. v1, v2 up to vn in V is called a basis of V if V is the span of v1, v2 up to vn, and these vectors are linearly independent. In other words, v1, v2 up to vn is a linearly independent spanning set of V. In this case, every vector in V can be expressed as a linear combination of v1, v2 up to vn, and no vi can be expressed as a linear combination of the others. For example, e1, e2 up to en form a basis of Rn. Indeed, the vector x1, x2 up to xn can be written as x1 times e1 plus x2 times e2 plus up to xn times en, so the span of e1, e2 up to en is the whole of Rn. Also, x1 times e1 plus x2 times e2 plus up to xn times en equals the zero vector implies that the vector x1, x2 up to xn equals 0, which means that the components x1, x2 up to xn are all 0. So, e1, e2 up to en are linearly independent. As a second example, the set 1, 1 and 1, 3 form a basis of R2. First, observe that 1, 1 and 1, 3 are not scalar multiples of each other, so they are linearly independent. Also, 1, 1 equals e1 plus e2, and 1, 3 equals e1 plus 3e2, so e1 equals 3/2 1, 1 minus 1/2 1, 3, and e2 equals 1/2 1, 3 minus 1/2 1, 1. So, e1 and e2 is in the span of 1, 1 and 1, 3. Now, for any real numbers x1 and x2, x1, x2 equals x1 e1 plus x2 e2, which is in the span of 1, 1 and 1, 3. Hence, R2 is equal to the span of 1, 1 and 1, 3. As a third example, let V be a vector space of polynomials of degree at most d. In other words, V is the set of polynomials ad times x to the d plus ad minus 1 times x to the d minus 1 plus up to a1 times x plus a0, where each ai is in F. Clearly, x to the d minus 1 up to 1, they span V. To show that x to the d minus 1 up to 1 are linearly independent, suppose lambda d times x to the d plus lambda d minus 1 times x to the d minus 1 plus up to lambda 1 times x plus lambda 0 equals the zero polynomial. Since this polynomial must be equal to 0 for all values of x, we must have that all the coefficients are 0. In other words, lambda d minus 1 up to lambda 0 are all 0. We conclude that x to the d minus 1 up to 1 is a basis of V. Note that there is more than one basis. For example, another basis is x to the d plus 1, x to the d minus 1 plus 1, up to x plus 1 and 1. Now let's prove a proposition. Let v1, v2 up to vn be a basis of V. Then any vector v in V can be written uniquely as v equals lambda 1 times v1 plus lambda 2 times v2 plus up to lambda n times vn, where lambda 1, lambda 2 up to lambda n are in F. To prove this, suppose V can be written as two linear combinations of v1, v2 up to vn, namely lambda 1 v1 plus lambda 2 v2 plus up to lambda n vn, and mu1 v1 plus mu2 v2 plus up to mu n vn. Then, bracket lambda 1 minus mu1 times v1 plus bracket lambda 2 minus mu2 times v2 plus up to bracket lambda n minus mu n times vn equals the zero vector. Since v1, v2 up to vn are linearly independent, all the coefficients must be 0. In other words, lambda 1 equals mu1, lambda 2 equals mu2, up to lambda n equals mu n, which completes the proof. Now let's prove an important lemma. Suppose V can be spanned by n vectors. If a set of m vectors in V is linearly independent, then m is less than or equal to n. This means that the number of vectors in a linearly independent set must be less than or equal to the number of vectors in a spanning set. To prove this, let V be the span of v1, v2 up to vn, and u1, u2 up to um be a linearly independent set in V. Since u1 is in V, u1 can be written as lambda 1 v1 plus lambda 2 v2 up to lambda n vn for some lambda I in F. Note that u1 is in a linearly independent set, so it must be non-zero, so not all of the lambda i's are 0. By reordering the vi's if necessary, we may assume that lambda 1 is non-zero. Then v1 equals 1 over lambda 1 times bracket u1 minus lambda 2 v2 minus up to lambda n vn. This is in the span of u1 v2 up to vn. This means that V is the span of u1 v2 up to vn. In other words, we can replace v1 by u1 in the spanning set, and this set still spans V. Now, u2 is in V, so u2 can be written as a1 times u1 plus mu2 times v2 plus up to mu n times vn for some a and mu I in F. Now, u1 and u2 is a subset of u1, u2 up to un, which is linearly independent. So, the set u1, u2 is linearly independent, which means that mu I is non-zero for some I. Similar as before, after reordering the vi's if necessary, we have that V equals the span of u1, u2 up to vn. In other words, we can replace v2 by u2 in the spanning set, and still this set spans V. Now, if m is greater than n, this procedure continues until V equals the span of u1, u2 up to un. But un plus 1 is in V, so un plus 1 can be expressed as a linear combination of u1, u2 up to un. This contradicts the linear independence of the ui's. Hence, m must be less than n, and this completes the proof. Now we can prove this important theorem. All bases of V have the same number of vectors. In other words, if v1, v2 up to vn, and w1, w2 up to wm are bases of V, then n must be equal to m. For the proof, we know that V equals the span of v1, v2 up to vn, and w1, w2 up to wm is linearly independent. So, by the previous lemma, we know that m is less than or equal to n. On the other hand, V is the span of w1, w2 up to wm, and v1, v2 up to vn is linearly independent. So, by the previous lemma again, n is less than or equal to m. This means that n is equal to m, and this completes the proof.